talk now about why magnetic fields occur. Whenever there is a moving electrical charge, we know that those electrical charges respond to magnetic fields. It turns out that electrical charges also cause magnetic fields whenever they move. So let's just start off with a generic formula so that we can figure out where this comes from. All right, so for a straight current carrying wire, this is kind of the generic standard formula that we would use to calculate the magnetic field. Mu naught is your magnetic permeability constant, which is 4 pi times 10 to the minus 7. Teslas is the unit that we're going for, and then we have to cancel out the meters and the current. So a Tesla meter per ampere. Magnetic field, of course, is a vector. To determine the direction of the magnetic field, you just use the right-hand rule. In fact, this is the same right-hand rule that we've been using technically. Okay, so same sort of thing. We always put our thumb in the direction of those moving charges. Our palm would typically tell us the force, but instead the wire is going to go like right along our palm. And then the way that we curve our fingers, it's going to make a circle. Those magnetic fields created by charge-carrying wires are circular in direction. So here we've got a piece of wire carrying a current to the right. We want to know what the direction of the magnetic field is at point P. So when we do the right-hand rule, we put our thumb in the direction, okay, of the current, and then the way that our fingers curl around, all right, so on the top side of this wire, my fingers are coming up out of the page, okay, and then on the bottom side of the wire, my magnetic field, my fingers are pointing into the page. So the field lines are going to look something like that. Okay, making a little circular field there. To figure out the magnitude, we just plug into this formula right over here. So our magnetic field is going to be equal to 4 pi times 10 to the negative 7 times our current, which was 13, divided by 2 times pi times our radius. So this right here is 3 meters away. When we crunch that all together, we get 86.6666 repeating microtesla. So at all points that are 3 meters away from this wire, this is the magnitude of the field at point P, assuming point P is in the same plane as the wire. That's going to be directed up out of the page. So we take this existing wire, all right, one that's got field coming out on top and in on bottom, and so now we placed yet another wire carrying current going through point P. So just to recall, right, the magnetic field produced by our original wire is coming towards us, above it, and then away from us into the page below us, like so. At this point, we just use our original right-hand rule to figure out the direction of the force. So this wire is within a magnetic field coming up out of the page. So we put our thumb in the direction of the current, we put our fingers, hello, in the direction of the field, and then our palm direction, okay, it's pointing down, like so. And then the magnitude of that force is going to be IL cross B. This into out of the page is always going to be perpendicular to anything that's on the paper, so that's really easy. We have a 90-degree angle there, which is ideal. So we get the current through this new wire, which is 50. okay, the length of this new wire, which is 100 meters, okay, times this pre-existing magnetic field that we calculated right here. And we get a force of, sorry, repeating, newtons pointing downward. What conclusion can you make about the force on the bottom wire? Oh, well, hold on. The presence of this wire here on top, well, it's also going to generate a magnetic field in very much the same manner as before. So I'll indicate what's going on here in, let me pick a distinguishable color, in red. Okay, so this wire here on top is also going to be generating a magnetic field that is out of the page above us into the page below the wire. So at, let's say, this point right here, right, this is experiencing a magnetic field into the page. We can do the same kind of thing. And so B here is going to be caused by this top wire, which is mu naught times I top over the radius, which is 3. So you see we have this same expression here. It's just these currents that have flip-flopped in location. Okay, it's still multiplicative. The order doesn't really matter. We end up with the same value. And if we were to do this, so the bottom wire of the current is going to the right. Okay, my field is pointing into the page, so I got to point my fingers downward, and my palm points upward. So, we have two forces that are the same size, equal in size, opposite in direction, acting on different objects. This is a third law pair. Okay. So in general, if we've got two wires that are carrying current in the same direction, this is always going to be an attractive force, right? Those magnetic fields are always going to be generated like this, either out of the page on top, into the page on the bottom, or vice versa if the current is flowing the other way. Okay, but they are always attracting. Okay. The next page. Here we have two wires that are opposite in direction. We haven't really talked about what to do with magnetic fields. Like, do they add, do they subtract? Is it more of like a voltage thing, or is it more like an electric field thing? It is a field, so you would use vector addition there. Usually they try to keep the magnetic fields pretty simple. Usually they're not going to be at any kind of weird angle, but if they are, you've got to break it into components and add up X, Y, and Z components of that. So here we've got one wire with current directed to the left, one wire with current directed to the right. We want to know the magnitude and direction of the magnetic field at point P. All right. So for this wire here on top, all right, I put my thumb in the direction of the current. I kind of wrap my hands around this wire. On the top side, my magnetic field is directed into the page. On the bottom side, my magnetic field is directed out of the page, like so. So it's going to go, if you were to actually sketch them out, something like that. Okay. It is going to be exactly the opposite for this one over here. All right, so just for practice, you put your thumb in the direction of the current, the way that your fingers curl around. So here on the top side, my fingers are pointing up out of the page. And on the bottom side, my field is directed into the page like so. So this one is going to be going this way. Not my finest work. So at point P, we've got both the top wire and the bottom wire producing magnetic fields that are coming out of the page. So this is going to be extra big at point P. So both of those are pointing out of the page. To figure out the magnitude of each one, we use that magnetic field formula that we haven't yet derived, but we will. Okay, so there's that. When you crunch that all together, 5 times 10 to the negative 7 Tesla for the one on top. This is going to be 8.67 times 10 to the negative 7 on the bottom. And so you just add them, which is 1.37 micro Tesla pointing out of the page. In the above sample situation, where is the magnetic field 0? So these magnetic field lines, I've only drawn like the 2 points, right? But as we continue, right, everything above this bottom one has a magnetic field, or has a component of the magnetic field that is out of the page due to this bottom wire, right? It's going to get much, much weaker as it goes, since it's an inverse relationship. From this top wire, everything underneath that top wire, there is going to be a magnetic field also trying to point out of the page there. So our magnetic field is going to be smaller above the top wire and below the bottom wire. But since these currents are unequal, we're only going to have a 0 on one of the sides, and it's going to be up here on top, right? Since this current is bigger, right, the magnetic field that's being produced by this wire is bigger, it's going to be able to counteract these into the page field components caused by the top wire. So we know that it's got to be above the top wire. And the magnitude of the two fields are going to have to be equal, right? Because they're going to have to cancel each other out. One's going in, one's going out. Okay. So to mathematically figure this out, let's measure from the top wire. So mu naught I top over 2 pi r, where r is measured above the top wire, and that's going to be equal to mu naught times I bottom over 2 pi. And so the total distance that this point is going to be, it's going to be r plus 7, right? R is how far it is away from the top wire, and then plus an additional 7 more to get us to the bottom wire. Okay, and you would just solve that there. Okay. Moving on. Now, this formula probably looks suspiciously like Gauss's law for electricity. If you recall, Gauss's law for electricity says that Q over epsilon naught is equal to the surface integral of E dot dA. Okay, so if you recall, for our Gauss's law stuff, we made this Gaussian surface. It was kind of this 3D balloon animal kind of thing. We made it so that the electric field lines were parallel to the area vector, or another way of thinking about it, the electric field is poking through your balloon animal at a 90-degree angle. Okay, that's what it means to have this dot product there. And it's actually not calculus. You just take the surface area of your Gaussian surface and you call it good. Your electric field is uniform and is constant at all of those points. So that's Gauss's law for electricity. This is called Amperes Law. Pretty similar in shape. This is going to be a ds instead of a dA. We'll talk about that here in just a moment. I want to talk for just a minute about Gauss's law for magnetism, because that has some interesting implications. Okay, Gauss's law for magnetism says that B dot dA, the surface area integral of that, must equal to 0. Well, what does this mean? How do you apply it? You don't really apply it. The idea here is that there are no magnetic monopoles. Okay, magnetic monopoles don't exist. Which kind of makes sense, right? If you imagine, a little particle of charge that's moving forward, well, one side, or both sides are always moving forward. There's a leading end and a trailing end. You can't have one without the other, and so you can't isolate a pole of a magnet. It's always going to be that duality of a north and south pole. So that's Gauss's law for magnetism. Faraday's law of induction we will talk about soon. This is going to be useful when we talk about generators. But first, we got to establish Ampere's law, and we have to practice Ampere's law just like we practice Gauss's law so that we can get good at it. So sample problem number 1, use Ampere's law to derive the magnetic field at a distance r from the center of a wire of radius carrying current I naught, where the radius of our Amperian loop is larger than the radius of the wire. Okay, so with Gauss's law, we talk all about these Gaussian surfaces. When we talk about Ampere's law, we talk about an Amperian loop, okay, which is it's a circle as opposed to like a 3D shape. Generally a circle, I should say. So as we are trying to set this up, we say B dot ds is equal to mu naught times I. So the idea of what's happening here is we draw a path that is always parallel to your magnetic field. Okay? So a complete path. Okay, so like how with Gauss's law, we drew our Gaussian surface so that the electric field lines were parallel to the area vector, as in they poked through our balloon animal at 90 degrees. The same sort of thing going here. So this is a wire, it goes, it's going into the page, right? And so the current is flowing down, okay, into that paper. If we were to create an Amperian loop around it, well, we put our thumb in the direction of the current, and then the direction that our fingers go is going to be the direction of the magnetic field. And so our magnetic field is going to be going around, like this. Okay, and then the farther out we go, the weaker and weaker that field is going to get. All right, so, at the beginning it might start something like this, and it's going to get, there you go, less and less dense in the distribution as we go, if we were wanting to model it that way. So this magnetic field that goes all the way around, this is perfect. My Amperian loop is a circle with a radius of 2 pi times little r. So let's go ahead and do that. So what this thing means, right, we have a closed loop. It's, again, not calculus. You just pop in 2 pi r. and that's going to be equal to mu naught over I. And so we get mu naught I over 2 pi r, which is the first equation that we looked at right at the beginning. I said, hey, this is like the generic, this is the standard, this is like the default. Usually you can use this in order to figure out the magnetic field around a long straight wire. Okay? Just like with Gauss's law, we can make our Amperian loop be within the object itself. So here we're trying to figure out what's the magnetic field actually within this current carrying wire at some radius that is less than the radius of the wire itself. And just like with Gauss's law, we have to set up a little ratio, okay, to figure out what the current enclosed is. Right? Gauss's law is all about charge enclosed. Ampere's law is all about the current that is enclosed within this loop. So d dot ds is equal to mu naught times I enclosed. Okay, the left side of this is going to be exactly the same as the other one. So this is the circumference of our Amperian loop. Okay, our Amperian loop is running perfectly parallel to the magnetic field that's getting produced. Okay, so that's why we can essentially pull out the b term, and then the integral of ds over the whole entire thing, that's what the circle means, is going to be the circumference, is equal to mu naught over. All right, so we've got a ratio going here. Let me doodle this out to the side. So we know that the total current, let's say, is I naught, right, over the cross-sectional area of the wire, which is a circle, so pi r squared for the whole entire wire, sorry. So capital R there. And that ratio is going to be the same for the enclosed wire. It's going to be pi times little r squared. So I'm trying to isolate I enclosed. Those pi's will go away and multiply this by r squared. So I would get that. Okay. And I'm able to cancel out one of these r's, like so. So I get my magnetic field is equal to mu naught I over 2 pi big R squared times a single r, like that. Of course, I want you to make a graph. So if I were to make a graph of a magnetic field as a function of radius r, where here is big R, right, the length, sorry, not the length, the radius of the wire. Okay, when we are within the wire, right, this is our variable, it's linear. This is going to be a nice linear line. And then once we are outside of the wire, that magnetic field is going to decrease in strength like 1 over r. Okay, so magnetic field is directly proportional to the radius while you're inside the wire, and it is inversely proportional to the distance, okay, from the center of the wire if you are looking at the outside. Okay, now, solenoids. Very cool, sort of. So the solenoid is a coil of wire. When a current runs through the wire, it causes the coil to become an electromagnet. You can imagine, we were just talking about, what were we just talking about? Well, we can take a moment here and talk about loops of wire. A solenoid essentially intensifies a magnetic field. If you were to stick something metallic, generally iron, the classic example is like you stick a nail inside your solenoid, that is going to strengthen the magnetic field. That's going to affect the magnetic permeability mu naught. You know how when we have a dielectric and a capacitor, it's kappa times epsilon? Okay, similar here for a iron core solenoid. It's going to affect mu naught. Okay, I don't actually know what the constant for that is, what symbol it's for. But, so here we have the solenoid that is hooked up to a battery. I'm just going to pick a direction. Let's say that from here, this coils this way like so. So it goes this way around the back, and then this way around the front, and it does that all the way through, all the way through, all the way through, all the way through. So that, how did I have this? Yes. So this way and that way, like so. So this comes down and joins like that. Okay. To figure out the direction of the magnetic field, maybe before we do that, let's talk again about our two wires with opposing currents. So let's say, I've got the current going this way and this one, and that way and this one. Okay, we kind of make a little bit more of a leap, and let's go ahead and make it, one closed loop like so. Okay, let's talk about the magnetic field inside the square, outside the square. So for this top wire, right, current goes this way. On the top side, we've got field coming out of the page. Here we've got field going into the page. And then, so everything below this, right, there's going to be, all right, a into the page component of the magnetic field due to this top wire. Okay. We can kind of do the same thing for the bottom wire. So the current's going this way. When my fingers dip inward over here, and then like so. And so, of course, everything, the magnetic field caused by this wire is going to decrease in strength above it, right? And then you can kind of extrapolate looking at those sides. Okay, the interior of this loop is extra super duper strong in the inward direction. Okay, we've got a really big inward magnetic field. Here on the outside, we always have these two magnetic fields opposing each other. So the magnetic field ends up being negligibly small on the outside at like a decent distance away. Okay. And so if the magnetic field is negligible outside of the loop, then really we're just looking at what's going on inside the solenoid. So this is a little weird. Let's go ahead and draw an Amperian loop here. So the shape can be pretty arbitrary. All right, so hey, look at that. That's my Amperian loop. Looking at my picture, the magnetic field is going to be pointing this way through the solenoid. All right, so you just do right-hand rule, and you think, okay, what when my fingers dip inside the solenoid, which way are they pointing, to the left or to the right? So they're pointing that way, to the right. When we do Ampere's law, we say B dot ds is equal to mu naught times I enclosed. Okay, this dot product means, again, that you are looking to multiply the part of the loop that is parallel to the magnetic field. That's what this dot product is. Okay. And so, there is, if we make one complete loop, well, we want this side to be going this way. Right, so this is perfectly width, and then none of the rest is width. And remember, out here, the magnetic field is negligible, so it's not going to be important. So it's just this length, which let's call that length L, that's going to be important. So as far as I enclosed, each one of these coils has the current I naught going through it. I don't know how many coils there are. Let's say there is n number of coils, like so. And so the strength of our magnetic field is going to be mu naught times N times the initial current divided by L. And then there's this kind of shortcut where this N over L, it's the number of turns per unit length, which we call lowercase n. Okay. Sometimes it's called turn density. Okay. We have kind of already talked about magnetic field around a loop of current. You put your thumb in the direction of the current and you curl your fingers around the direction. Wait. Oh, no, they do this in the most hateful way ever. Disregard that, right? Put your thumb in the direction of the current. Okay, it's like you're holding this coil, right? Like so. So you put your thumb in the direction of the current, and then the direction that your fingers poke through, right, is going to be the direction of the field. Okay. So let me see if I can very badly draw what I mean here. So here we have this coil. Imagine it's on the page. I put my thumb in the direction of the current, and then so here, right, when my fingers are on the outside, let me attempt my best to draw. So this is my wrist. There's my thumb. Right, and then my fingers are pointing up. There we go. Yeah, best hand drawing ever. So that means here on the outside, right, the magnetic field is coming out of the page due to this little segment of wire right here. Okay. Over on this side, let me see if I can't do it the other way. So my thumb is pointing down over here. Okay. From this angle, my fingers are dipping into the middle, okay, of that. So here's my thumb. There's my wrist, I guess. And then my fingers are now pointing into the page. Use your imagination. It's all good. Does that make sense? So to figure out the directions, you do that. Generally, when you're talking with a loop, the inside of the loop is going to have the strongest magnetic field. Generally, you can say that the magnetic field on the outside of the loop is going to be much, much smaller in comparison. Okay, much, much smaller in comparison. All right. Last sample problem. It is about a toroid. The toroid is you take a solenoid and you wrap it into a donut. And Amperes Law works super great with this. It's quite delightful, I guess. So Amperes Law says that the path integral multiplied by your magnetic field is equal to mu naught times I. If you make your Amperian loop small, so let's say that R is less than A, right? So it would be in here. Well, do any of those wires pass through that? No. There is no current enclosed. So there is no magnetic field in the center of the donut. Okay? Same thing if we make our, well, almost the same thing, if we make our Amperian loop really, really big. Okay? We've got essentially current going into the page, current coming out of the page. It always ends up canceling out. So like our net current into and out of the page, left and right, all of that good stuff, ends up being 0. As well. Okay? So this one's too small, this one's too big. The correct size for our Amperian loop, it's just right in the middle of our toroid. So looking at this picture, let's see if we can't figure out which way this is going. So let's take a look at this loop right here. So the side of the loop that's close to us has the current going to the right. So there we go. If I arrange my fingers so that they're tucked into the loop, my fingers are pointing this way. So my magnetic field is circular. It's going all the way around on the inside of that toroid. So to figure out the strength of this magnetic field, so the circumference of my Amperian loop here is 2 pi r, right, where r is in between the inner radius A and the outer radius B. And that's equal to our permeability constant times our I enclosed, just like before. I guess I could count up how many loops this is. Let's just say that it's n number of loops times the current that is flowing through. And we rearrange. Like so. And we are done. Takes a little bit of practice, just like Gauss's law. You definitely prefer your problems to use Amperes law over our next topic of discussion, which is going to be the Biot-Savart law.